All right, so we'll play a little bit more around with the idea of the fundamental theorem of line integrals, which was the extension of the fundamental theorem of calculus that we could use for line integrals, right? So if we had, for example, the integral of the over the curve of your function, if you had the integral over a curve of the gradient of a potential function dotted with displacement that was equal to that function evaluated between the upper limit b and the lower limit a in a parameterization of whatever curve you're dealing with. So we looked at how that was applicable only to the conservative vector fields. So we are going to kind of examine conservation a little bit more formally. Kind of noted how conservation is derived as something that implies path independence, allows you to have a path independent line integral. So if I had a conservative force on this plane that acted wherever I'm taking my line integral, if I'm going from point A to point B here, so I've got A there and B there, then I'm taking a path independent line integral, then it doesn't matter if I go that way or if I go that way. These will both be the same. Or I could alternatively say that the closed integral of the vector function of the vector field dotted with dr over the curve is equal to 0. So if I go in any closed loop, then the work done will be 0. So what we want to do today is examine conservation, conservative vector fields, and then use it to be applied in the conservation of energy formalism, which is quite important to look at. So let's do that now. So the definition for a conservative vector field is that if F has components P and Q, and let P and Q be functions of x and y. So these are both functions of x and y, and they're on a domain D. Now, if I have that the cross derivative, so the derivative of the x component, p, with respect to y, that's equal to the derivative of the y component, q, with respect to x, then f is conservative. So that seems simple enough. Let's try an example just to test ourselves out. Let f be equal to 3 plus 2xy as its x component, and x squared minus 3y squared as its y component. Is it conservative? So if I take the derivative with respect to y of the first component here, then I get 2x. This goes to 0, and then the y gets killed. If I take the derivative of the y component with respect to x, then I will have that this y component gets killed, and then this 2 will go down with the power rule. And I get 2x. So thus I have, because partial yp is equal to partial xq, f is conservative. So we have a conservative vector field on our hands. So that's an easy way to check, okay? So now let's examine this in the context of conservation of energy. So let's have that the force F is a vector field, and it acts on an object modeled by the distance function r of t. So that's its position function, r of t. Now you're going to need to remember a couple of quantities back from when we were talking about vector functions in the first unit of the course, because we discussed some important physical properties that we can use to manipulate acceleration, velocity, and position. So anyways, what we can do is we can model this with Newton's second law, and also just model that our endpoints are going to be A and B. So if I use Newton's second law, we're going to assume that the force is a function of position. So F of r of t is equal to mass times acceleration, or the second derivative of r of t. So if I want to find the work, then that's equal to the integral of f dr, which can be equated to the integral between a and b of the force, and then times, if you remember from a couple videos ago, when we're taking the line integral over the vector function, we use the derivative attached to the dt of the vector function. So we have times r of t dt, or r dot of t dt. And we can use Newton's second law so that we have the integral between a and b of m of r of t double dot dotted with r dot of t dt. And then we had some formulas back from earlier units about the relationships between the acceleration and velocity. And we can rewrite this as 1/2 of the mass times the integral between a and b of the derivative of r dot of t dotted with r dot of t dt, which is equal to 1/2 of the mass times the integral between a and b times the derivative of the r dot of t squared magnitude dt. So we can rewrite this using the fundamental theorem for line integrals. And we note that, or well, because we're reversing the derivative, we can rewrite this as 1/2 times the mass times the magnitude squared of the velocity evaluated at b minus the magnitude squared of the velocity evaluated at a. This is equal to the kinetic energy, the change in the kinetic energy. We define the kinetic energy, T, is equal to 1/2 of mass times velocity squared. As you can see, that's what we've got in here. Okay, so we've done that for kinetic energy. Now let's look at potential. So we know that F is conservative, so there needs to exist some potential function. So we let the potential function V, the potential energy V, be such that if I take the negative gradient of the potential energy, I get the force. So therefore, the work is equal to the integral of f dr, which is equal to the negative integral, the gradient of the potential energy, dr. Then I can use the fundamental theorem of line integrals directly to get negative potential energy evaluated at one endpoint minus the potential energy evaluated at the other endpoint. So I get negative change in potential energy. So we have this nice thing where we've got that the work is equal to the negative change in potential energy, which is equal to the positive change of kinetic energy. So what we can deduce here, we can manipulate this equation so that we get the kinetic energy plus the potential energy at the initial point plus the kinetic energy, or is equal to the kinetic energy plus the potential energy evaluated at the end point. So that is the conservation of energy. This is an invariant quantity that we call the total mechanical energy. It will be the Hamiltonian when you keep studying this sort of stuff, because the Hamiltonian is equal to the kinetic plus the potential energy. But that's for later, but right now we will use the mechanical energy. E is equal to T plus V. Okay, so we try an example. We say that the force is equal to C times R over R magnitude cubed. And we're moving from some initial point P, we're keeping this very arbitrary, from P1 to P2. And we're going to say that the distance here is D1 away. The distance here is D2. So we're going to work in kind of the radial coordinate system here. We're just going to be measuring the distance away from something. And we've got that the forces are dependent. It's dependent on the distance away from the from where we are. Now, what's important here is what we have is an inverse square law. These inverse square laws pop up everywhere. We just have the r cubed and the r on top just because we're having it in vector form. You'd recognize this a lot better as force is equal to or proportional to 1 over r squared. That works for electromagnetism and it works for, it works for electrostatics and it works for gravity. Anyways, let's see if we can find the work done between P1 and P2, and we'll leave it in terms of the distances, right? So what we've got here is we want to find the integral, I want to find the line integral over the contour of f dr. And this, using the fundamental theorem of line integrals, is equal to the potential evaluated at B minus the potential evaluated at A. and then we're going to negate that when we actually have the potential energy. So, we will negate it. Anyways, what we have to do now is to find the potential function for this force. So the potential function for the force is pretty easy to find. We have something proportional to 1 over r squared, and our potential function is going to be the integral of 1 over r squared. So we're going to get negative c over r, right? So what we've got is negative c times 1 over r evaluated at b and then a. So what we get is negative c over a, or c, we get positive c over a minus c over b. And we can rewrite this in terms of the distances away, so we get c over d1 minus c over d2. So I hope that was helpful in explaining how the conservation of energy works and how we can do some worked examples with them. It's fairly simple. In the next video, we're going to look at taking in more complicated line integrals using Green's theorem, one of the many theorems, integral theorems of vector calculus that we'll be using. And then after that, we're going to move away from line integrals and start talking about surface integrals, which is the natural next step. And that will really be the capstone of all of calculus. All right, so we'll see you then. Thank you.